My name is Jean-Luc Brousseau. I'm the International Sales Manager for Europe, and I will be presenting the first half of the meeting. The second half of the meeting will be presented by Dr. Jean-Baptiste Bossa, who is the Product and Application Specialist in charge of Europe. So let's start again, and thank you again. This webinar will be about 30 minutes, and then we'll go to the questions. The webinar is about one of the three new European standards that were adopted by the Water Framework Directive. The first one we're talking about, or this one in this webinar, is about PAH, Polycyclic Aromatic Hydrocarbon, PAH. The Water Framework Directive was adopted in 2000 to monitor water pollutions. And this is water in lakes, in river, and groundwater, and every kind of water. So it's called whole water. So in this European standard, it's about whole water. The list of priority substances was established the following year in 2001, and that was known as the Annex X. It took about 7 years to find the concentration, the maximum concentration or the limiting concentration for those 33 priority substances, and this is called Annex 2. The name was changed from Annex X to Annex 2. So what are the 33 priority substances? This is the list. There is 33, but you can see in red, 2 is anthracene, 15 fluorantine, and number 28 is for polyaromatic hydrocarbons, and there are 5 different aromatic hydrocarbons that my colleague will discuss a bit later on. These methods, these analysis of the pH are on those 5 polyaromatic hydrocarbon on number 28, plus the 2, number 15 and number 2, so a total of 7 PAH. The other methods that were adopted were for OCP, organochlorine pesticide, and it's in the next slide. Let me show you. The method at the top right, you can see the method EN 16691 here. And this method is what we're talking about, the determination of selected, only 7, polycyclic aromatic hydrocarbons, the PAH, in whole water sample. Whole water, again, is river water, it's lake water, underground water, and all kind of water, or even drinking water. The method to analyze, to extract is solid phase extraction with SPE-disk combined with a gas chromatography mass spectroscopy, GCMS system. The other methods that were adopted recently were EN 16693 and EN 16694. These two methods are very similar, which it requires SPE-disk combined with GCMS to analyze this the whole water samples. The fourth and final one is 16692, is about TBT, tributyl tin, and this is still in a provisional application. One thing I forgot to mention is the first one, 16691, is on PAH, polycyclic aromatic hydrocarbon. The second one is on organochlorine pesticide. And the third one is on polybrominated diphenyl ether, PBDE. So if you're equipped to measure already with solid phase extraction using SPE disk, you can use those three methods already. So let me tell you a bit about what are PAH. PAH stands for polycyclic aromatic hydrocarbon, and they are made of two or more fused aromatic rings, making them highly lipophilic and highly soluble in non-polar organic solvent. The term PAH refers to a group of several hundreds of organic compounds with various structures and toxicities. PAHs have, in general, high melting and boiling point. They are therefore present as solid material in nature. They have also low vapor pressure and low solubility in water. Larger pH including more than 6 fused aromatic rings are less water soluble and less volatile than smaller the pH, and therefore they pose more risk in nature. They are more persistent. The problem with pH is because pH have been shown to cause carcinogenic and mutagenic effects. So that's why it's important to monitor and to have low quantity, low amount of pH. Where do the pH comes from? They are from found worldwide, everywhere, and they are emitted from different sources, including natural sources like forest fires, volcanoes, and crude oil. Actually, PAH is composed by weight 30% of crude oil. Other sources triggered by human include petroleum industries, electric power generation, pyrolysis, and incomplete combustion in general, home heating, and finally production of coal and asphalt. The major route to exposure to pH is from breathing indoor and outdoor air that is polluted, but also these pH will find their way into our water and soil, and it can contain non-negligible amount of PAH. The European Standard 16691 2015, the standards specify the method for the determination of those 7 PAH, and it's working with an upper limit range of 2 ppb, which is also 2 micrograms per liter. And this is valid for drinking water, underground water, river and lake water. So the official date of publication of this standard was in March 2016. So let me go to the next slide. And this is the first page of the European standard. And you can see that the title is in English, but you have at the bottom left the title in French, bottom right in German. It's been translated in a few languages at least. So again, the date at the top here says August 2015. That's when it was finished writing, but it was in March 2016 that the standard was adopted. And I think this is it for my part. I'm going to put the information, the presentation to Jean-Baptiste.
Okay, thank you, Jean-Luc, for this very nice introduction. Good morning, everyone. My name is Jean-Baptiste Gosselin, and I will continue this webinar. Here are depicted the chemical structures of the C-then polycyclic aromatic hydrocarbon, or PAH, and ranging from anthracene on the top left, which is the simplest one, which contains 3 fused aromatic rings, to benzopyrrolane, the structure you can see on the bottom right. These 7 PAH have been identified as being of greatest concern with regard to potential exposure to human beings. They are actually qualified as persistent organic compounds for the environment. Therefore, the methods to determine PAH in water should be accurate and sensitive enough to allow the detection of trace amounts in various volumes of water. Actually, the limitation for these 7 PAHs is 0.1 microgram per liter, except for benzopyrene, which concentration is limited to 0.01 microgram per liter. Oops. So why using solid phase extraction disks? This slide shows an extract of the European standard EN 16691, page 10, section 8, procedure for sample preparation. It is clearly written, do not filter the samples, hence ruling out liquid-liquid extraction techniques and solid phase extraction cartridges by which it is mandatory to have clean samples. As mentioned earlier by Jean-Luc, polycyclic aromatic hydrocarbons are highly soluble in organic solvents and poorly soluble in water. Any PAH adsorbed on particulates must be extracted along with the one dissolved in the water sample. An external filtering of those particulates may run the risk to underestimate the actual amount of PAH in the water sample. So what is actually the difference between the cartridges and the solid phase extraction disks? SPE disks are more efficient for larger sample volume, up to 8 liters, and for samples that may contain particulates such as sediment, clay, or soil. As a consequence, with a solid phase extraction disk, one can use faster flow rates up to 200 milliliters per minute, process large volume faster without any breakthrough. The diagram on the left shows typical cartridges with packing materials ranging from 40 to 60 microns. And you can imagine the systems like large rocks stored in a jar. If you flow the water samples too fast, you may run the risk to have channeling, meaning that the water sample can pass through without making contact with a particulate, and you will not get the adsorption you are looking for. In contrast, solid phase extraction disk typically uses 5 to 10 micron particles for the retention, therefore much smaller than the solid phase extraction cartridges. Imagine this time the system like sand stored in a jar. If you flow now the same water samples, contact with particles occurs, and you will get the adsorption you are looking for, and breakthrough is not possible anymore. This means also that we can use faster flow rates with solid phase extraction disks. If particulates are present in the water sample, they might compromise the flow through the solid phase extraction disk. In that specific case, we recommend to use an easy flow or fast flow sediment disk holder. This disk holder holds a regular 47 millimeter size solid phase extraction disks in the bottom, allowing also pre-filter from 5 to 1 micron to be placed on the top. These pre-filters protect the SPE disk from clogging, contain the particulates, and allow the water sample to flow through the solid phase extraction disks. Since the particulates are not discarded by an external filtering, the eluting solvent rinses the particulates together with the original sample bottle, hence ensuring that any analyte adsorbed on the particulate matter and inside the inner wall of your empty bottle will be extracted along with the water sample. So this is a tool for solid phase extraction on polycyclic aromatic hydrocarbons we have been using in our labs. The extraction of PAH from water was done using the SPE-disks 4790 extractor systems together with the Atlantic divinyl benzene or DVB solid phase extraction disks. Divinyl benzene is a polymeric solvent. These solvent materials do not contain silica sulfates like the regular C18 solvent materials, but it is entirely organic polymer with a more hydrophobic surface. Therefore, DVB disks are very effective in extracting highly lipophilic compounds like your PAH. In addition, this solvent can go completely dry during the pre-wet steps and still be as effective without compromising the retention of compounds. This is the tools we use for concentrating the polycyclic aromatic hydrocarbons after extraction. The sample extracts were dried and concentrated using the dry vap evaporation system together with the dry disks. The dry disks, or hydrophobic membranes, were used to remove water from the sample extract. We evaporated around 100 milliliters of eluting solvent to an automatic endpoint of 0.9 milliliter. We then performed a solvent exchange with toluene by rinsing with 20 milliliters of this solvent. We finally evaporated to an automatic endpoint of 0.9 milliliter. It is not recommended to evaporate the extract to complete dryness, as losses of the free ring compounds may occur. Analytical tools for PAH analysis. In our labs, we use chromatography. So this is the 6890 model from Agilent, together with the 5975 mass selective detector, also from Agilent. But please note that any other brand could have been used. The extraction method summary is given in this slide. The first step is to transfer a 1 liter sample into a glass bottle. The next steps consist of verifying the pH to be between 6 and 8. We then spike deuterated internal standard with a concentration of 5 micrograms per milliliter into the sample prior to the extractions. We then, in the fourth step, spike targets in a lower concentration, this time 0.5 microgram per liter, into the samples. And we then incorporate the fast flow disk holder in case of heavily particulated or dirty samples. We then start extraction method programmed into the in-bridging controller that goes together with the 4790 extractor units. We can set the flow rate at about 25 milliliters per minute by setting the regulator to -4 inches of mercury, as recommended in the European standard EN 16691. Or we could also set the flow rate at about 100 milliliters per minute by setting the regulator to -24 inches of mercury, which is a normal running pressure with the 4790 extractor unit. And then finally collect the extract. So Here is depicted a table with the extraction method. The DVB disk needs first to be conditioned in order to be prepared to accept your water sample. The extractor system performs automatically three pre-wet steps using first methylene chloride or BCM, also known as the eluting solvent or the final eluting solvent you are going to use. Then acetone is used as a follow-up solvent to prepare the DVB disk to water. Finally, the disk is conditioned with water, and this will stop the pre-wet steps. The sample flows in another cycle from the original sample bottle into the disk holder very quickly, and then directly flow to the water waste. The PAHs are actually retained onto the DVB disk. The sample bottle is rinsed with the solvent also used for elution. This makes certain that any PAHs sticking to the inner glass bottle will be transported to the disk and eluted with the other analytes of interest. The disk is finally rinsed to ensure a good transfer of the PAH into your collection vessel. The same extraction method can also be visualized in a schematic way. The first step consists of conditioning the SPE disk with the final eluting solvent, then acetone, and finally finishing with water. During this pre-wet cycle, the SPE disk holder is shown in green because this is where action occurs. During the sample cycle, the sample bottle, the water inlet valve, and the solid phase extraction disk holder are shown in green. During the rinse cycle, rinse solvent is sprayed into the sample bottle, which drip down onto your solid phase extraction disk holder as displayed in green in this scheme. Finally, during the elution cycle with methylene chloride or DCM, the collection vessel is displayed in green. Now, extraction is done, and now it's time to concentrate your extract. Extracts were automatically dried and concentrated using the dry disk membrane to remove the possible trace amount of water. Evaporation and therefore concentration is achieved by heating under vacuum and sparging gas. In this case, molecular nitrogen is used as a sparging gas. After reaching a certain level, the heater turns off and the evaporation continues with vacuum and sparging gas only. An automatic endpoint detection to about 0.9 milliliter turns off the dry vap evaporation system and the concentration is over. The method specified approximately 25 milliliter per minute loading for the sample. For 1 liter of sample, this takes more than 40 minutes. The recovery are shown in this table. The PAH spikes recovery are excellent, as you can see, for the full range of compounds. The top part corresponds to your deuterated internal standard, and the bottom part corresponds to your actual PAHs of interest. Next, the samples are run with full vacuum, allowing the sample to pass through the disk at about 100 milliliter per minute. The recovery are shown in this table, and we can clearly see that the higher flow rate does not really impact the performance of the method. This allows the total time for 1 liter of sample to flow through the disk in about 10 minutes versus 40 minutes for the slower rate as seen in the previous slide. Now, samples with particulates. These slides actually demonstrate the performance of automated solid phase extraction of PAHs following the European standard 16691 with a more realistic water sample, in this case surface water taken from a pond and containing some particulates, as you can see in the pictures on the bottom right. The pond water was collected in two different bottles, spiked with targets and then processed in duplicate. The concentration values are shown in this table in microgram per liter units, together with the relative percent difference, or RPD. The relative percent difference between the two observed values are less than the generally acceptable value of 20%. The particulate present in the pond water did not impact the analysis either in speed of sample passing through the DVB disks or in recoveries of the analytes of interest. Now it's time to conclude our webinar. This work demonstrates the performance of automated solid phase extraction using solid phase extraction disks for the extraction of a full suite of PAH compound. Automated solid phase extraction using solid phase extraction disk complies with method requirements from the European standard EN 16691 from 2015, and therefore provide excellent recoveries between 70 and 110%. We could demonstrate with this webinar that automated solid phase extraction using solid phase extraction disks therefore meets the Water Framework Directive requirements. Should you need further information on the actual methods and performance data, we can provide you such information or documents. Thank you again for joining this webinar. Thank you for your interest. And we'll be really happy now, Jean-Luc and I, to answer any of your questions.
Thank you, Jean-Baptiste. Okay, we have a few questions at the time. Let's go back. And if I press return here, and you will have question and answers on the right-hand side. The first question we get is, can't I get the same result with SPE cartridges rather than disks?
Oh, excellent question. Cartridges have a small surface area and can easily clog with whole water samples containing particulates. The particulates can absorb some of the components of interest and should be included in the extraction process, which can easily be done with disks.
Thank you.
We'll go.
Second question. You mentioned Atlantic disk, but won't any SPE disk work?
Well, actually, Atlantic disks have some distinguished features to make them preferable. High-quality disk with pre-filter built-in SoFlow is maintained, and yet the particulate is captured for extractions. Second point is each lot is quality control tested to work with automation to better ensure lot conformity, and they are always in stock. For this specific application notes, we use a DVB disk, and should you use and follow this procedure, we can guarantee the recoveries that we have been showing in the previous slide.
Okay, any other questions? We're going to wait a minute to see if there's any other questions. There's a question about support. Maybe I can help with this. this is a new technique for us. How can we get support? Yes, indeed, this is a technique that might be new for you in Europe, but Horizon Technology United States have been working for more than 20 years in similar analytes. So this is something we've been doing for a long time. Our website has a large number of application notes for different disks and material. So an analyte, and you can download anything that you want. You might have seen in this presentation a couple of slides with application note references on this method 16691. In addition, we have local partners to help in most countries in Europe, and we have direct people like Jean-Baptiste here who are able to travel easily in Europe. We have also international service manager, Mr. David Gallagher, who is traveling to Europe and helping into installation and applications also. So yes, we have a full team of people in Europe, distributors, and a full team of local people. So no problem to help you with your application.